We've got Thursday, November 19th, 2020. We're going to be discussing two-way tables, the general addition rule, and Venn diagrams. So first, two-way tables and probability. When trying to determine probabilities involving two events, a two-way table can be used to display the sample space, so the probability calculations are easier. These are very similar to the two-way tables we saw with categorical data. For example, the college statistics class wanted to find out how common it is for young adults to have their ears pierced. They recorded data in two variables, gender and whether a student had their ears pierced. Notice these are actually both categorical variables, gender and whether or not someone had their ears pierced. All right, for all 178 students in the class, it's a big class. The two-way table displays their data. Here's our two-way table. All right, so again, it's very similar to the two-way tables that we've seen previously for categorical data. We have gender across the top, male, female, pierced ears, yes or no. We have our yes row, 19 and 84, total 103. No, 71, 4, total 75. Total between the row and the column, they should both add up to 178 and then get all of our students. All right. So we're now going to use this to talk about probability. All right. So let's do this example. We have a pen. That red's very good. So suppose we choose a student at random. Whoops. Hey, no. What did I do? Darn it. I hit something backwards. Here we go. All right. Suppose we choose a student at random. Find the probability that the student has pierced ears. Right, so the first one, looking at a student has pierced ears. So we're looking at our yes category, right? We're not considering male or female, so we're just looking at what's the probability, what's the proportion essentially that a student has pierced ears, right? That is a total of 103. Right, so the probability we have is 103 out of 178. All right. So okay, other thing we want to set up that kind of fits into the notation we've been using. Let's define two events. We have event A. Event A is going to say that the person is male. And that's because in our next few questions, we're considering only the male students. And event B is that they have pierced ears. All right. So this, if we want to fit it into our notation, is the probability of event B. All right, 103 out of 178. And again, we can leave this as just that fraction. There's no real need to convert it to a decimal. So this is fine. Part B is male and has pierced ears. So we're looking for probability of A and B. So I need the probability of the person being male and their ears are pierced. I need both things to occur. All right. Looking at male, right, and yes, we see that right here. These are the number of males in that statistics class that have their ears pierced, 19. So we get 19 out of 178. right? We have 19 outcomes that fit both conditions. Our last one here is male or has pierced ears, gives us more options. Right, we have P of A or B. So this emphasizes the difference between and or. All right. Or is more inclusive. We get more possibilities. So we can either be male or have pierced ears. So we have the total number of males, 90, and total number with pierced ears, 103, right? But here's a problem. In our previous lesson, we saw what happens when events are mutually exclusive or they cannot both occur at the same time. These events can. I have males that also have their ears pierced, right? If I just add up 103 plus 90, I get 193. I only have 178 students in the class. This is statistically impossible. I can't have that many students. Can't have more than the total, right? So this doesn't work. The reason it doesn't work is because I've counted these students twice. They were counted in the total of males and the total for pierced ears. I only want to count them once, but I have to subtract one counting of those 19 males from my total. And that leaves me with 174. That number works. That is less than my total. All right, so we get for this one, P of A or B is 174 out of 178. Right? So there we go. That's the way to use our two-way table to find our probabilities. Right? We have to be careful with that or situation because we want to avoid double counting values. So we have to be careful of that. We have to identify the things that might be counted more than once. Right? What questions do you have? Does anyone need a moment to write anything down from this slide? Please raise your hand. So let's look at our next thing here. So again, this graphic here illustrates the same thing that I was talking about, double counting, right? If I just add the probability of A and the probability of B, right, P of B plus P of A, I count these 19 people twice. We can't do that. And so that gets us to our general addition rule for these two events. Right? If A and B are any two events resulting from some chance process, then the probability of A or B equals the sum of those two probabilities, P of A plus P of B, minus the probability that both events occur at the same time, the and event. Which is what we did, right? We subtracted that P of males and pierced ears, that 19. Right? And that accounts for the double counting. Right? So we have the general addition rule for two events. The addition rule for mutually exclusive events, which we saw last class, which just said P of A plus P of B, This is just a special case of the general addition rule for two events. When events A and B are disjoint, or mutually exclusive, then P of A and B equals 0. And you're left with just P of A plus P of B. Okay, so if you're going to memorize or remember or know one of these rules, you need to know this one, because if the events are disjoint or mutually exclusive, it works out. And if they're not disjoint or mutually exclusive, it also still works. Right, so this is, I would categorize as the more important rule. Okay. Is there anything I can clarify about this? Does anyone need a moment to write any part of this slide down? Please raise your hand. Alrighty. So next, this moves us to Venn diagrams, which is what I tried to draw the other morning, and I failed miserably. But we're going to look at better examples. Two-way tables are one way to illustrate the sample space of a chance process involving two events. Another way to use a Venn diagram. Venn diagrams are used in other branches of mathematics, set theory to name one. Some standard notation and vocabulary have been developed. First, we have complement, which we were introduced to last class. If A is an event, then the outcomes not in A are A superscript C. And this is shown in the illustration where we have the event A in the middle. The complement of A is everything else in your sample space. That's not part of A. The next thing with Venn diagrams is they make really good visual representations of some of these vocabulary terms and these definitions. And if you're writing this down or drawing the picture, can you raise your hand, letting me know you need a moment more to write it down. Okie dokie. Next, mutually exclusive or disjoint. Again, this is a term from last class. If A and B are two events with no outcomes in common, then they are mutually exclusive or disjoint. In the illustration, the events do not overlap. So event A and event B are disjoint. They have no outcomes in common. The S, again, just represents the sample space. So this other area is every other possible outcome, not part of A or B. Anyone like a moment more with this slide to draw the picture or write the definition? A new term with some new notation is intersection. If A and B are two events with some outcomes in common, then they have an intersection. This intersection is the event A and B. In the illustration, the shaded area represents the intersection. Corresponding notation is A, this little like bridge looking thing, B. And you just read it as A and B or A intersection B. Okay, so this green shaded area in the middle, that is the intersection or the shared outcomes between events A and B. And so we have this common notation, a little arch. Okay. And can you raise your hand if you're writing this definition down along with this picture and need a little more time? All right. Last new term. We have union. If A and B are two events in a sample space, the union is the outcomes of both events. This union is the event A or B. In the illustration, the shaded area represents the union. So we see it's just everything between A and B. The corresponding notation is A, this kind of like U-looking shape. It's the flipped version of the and shape, B. And we read that A union B or A or B. Okay. So this kind of much better illustrates the difference between and or within probability and other fields of mathematics. If you'd like a moment more to write this down or draw the picture, again, please raise your hand. Okay. So then we're going to look at this pierced ear data again. We'll get through these. So using our new notation here, we once again have the event A represents a male, and B has pierced ears. Right? So we have our two events. And we have just the section of the table that we need. We don't have the totals. We can't remember. I think the total number here is 178 people. All right. So the amount of things in A and B, right, this we saw last time, that's going to have 19. So the probability of A and B, that 19 out of 178. So A and B we've seen, essentially. C says A and B complement. So I want to know, what does A have in common with everything that's not in B? Right? That leaves us with these four, not in B, and the 71 that's in A and not part of B. Right? But these four are also not in A, so they're not part of the intersection. I can only consider things that are part of A and not part of B. That leaves just the 71. So we have 71 in there. So the probability will be 71 out of 178. Any questions about that one?
Yeah, could you explain it again?
Yeah. So I first looked at the two events being considered. I have A male, or this yellow circle here, and B complement. B complement says everything not part of B, right? So I lose the 19 and the 84 because those are all part of B. The only thing that I haven't considered that's not part of B besides the 71 is the 4 that makes up the rest of the sample space. But to be in the intersection, I have to count the things that are part of A and also part of the complement of B. So the only thing I'm left with is the 71, right? That's not part of the intersection, right? It's kind of like we cut it off here, right? And is also in A. So I'm left with just the 71. These 4 don't count because they're not also part of A. Did that help?
Yeah, thanks.
Okay, you're welcome. So then we have to look at A complement, because the event A complement is everything not in A, which again leads us to, we get these 4 again, right? They're not in A. And, right, I essentially cut off and only consider the things in B, right? Because those are also not in A. Just like the last one, it needs to be not in A and part of B. So I'm left with just the 84. So the probability of A complement and B is the 84 out of 178. So now, lastly, we have A complement and B complement. So I need to consider everything not in A, which is the 84 and the 4, and everything not in B, which is the 71 and the 4, right? And I need to only look at the things that are in both. What is not in A and not in B, right? The 71 is not in B, but it's in A, so I can't use that. 19 is in both, right? So it can't be used. And the 84 is not in A, but it's in C, so I can't use, but it's in B, so I can't use that. That leaves just the 4. That's the only thing that's not in A and also not in B. So I get just the 4. Right. Representing essentially the number of students that are female, not a male, and don't have their ears pierced, right? These 4. All right, so because we can use complements, we only need the 2 events, right? We have A complement is female, B, and B complement is not pierced ears. So there's no need to make events C and D to represent the other options, right? In this case, because there's just male or female and pierced or not pierced. So we can account for all the events by just making 2, right? What questions do you have? Because I made a mistake. Thanks for calling that out, Jasmine. It's supposed to say 178 as well. My bad. Thank you. We'll fix that. And this goes back to one of my previous points in the class. Simple errors like arithmetic errors or just writing something down wrong are the most common. Most common type of error I made on exams and things in college, for sure. Usually most of my professors are really nice about it though, so that was good. But yeah, so thank you. All right, so yeah, the notation allows us to like do stuff a little faster. We don't have to write out the entirety of what we're talking about. We just say, hey, let this event be this, and this event be this thing, and now I can do all the stuff. All right. Any other questions? All right. So this is the end of the presentation. We're going to end the slideshow. We are going to go here. Yeah. All right, so, excuse me. There's the week 13 CYU that is now available. It is 4 multiple choice questions. This is just some things that you should know based on the lessons we've done. And yeah, it's all multiple choice. There's a 2-way table using a relative frequency histogram here to determine probabilities. Ooh, I need to do an example for this one. The question 3 has to do with making a sample space. When you have to choose a number of things from a set number of options. So I'm going to show an example of that real quick. And yeah, this is using some of what we just went over with the new notation and determining if events are mutually exclusive. So yeah, let me do this real quick. Let's, from Math 1. Yep. So let's suppose that you, let's say we have 4 people. We'll say Dave, Dan, Don, and Daryl. Why not? And I want to randomly select 2 of them to participate in, or I'm going to randomly pick 2 of them that are going to get like a free vacation somewhere, right? What are the chances right? What are the chances that Dan and Don are chosen? Right, so we're looking at what's the probability that these 2 guys get chosen. Right, to make this easier, to create my sample space, I'm going to label this Dave as 1, Dan is 2, Don is 3, Daryl is 4. So to create the sample space, I need to create all the different possible combinations of 2 people being chosen, right? So the easy way to do this is to say, okay, we can have 1 and 2, we can have 1 and 3, I can have 1 and 4, I can have 2 and 3, 2 and 4, or 3 and 4. I'm not double counting, the order doesn't matter. Selecting 2 and 3 is the same as choosing 3 and 2. Right, so I don't get extra options by changing the order of the numbers, right? So these are all the possibilities. I have 1, 2, 3, 4, 5, 6 possibilities. And these are equally likely, right? So picking 2 and 3, right? Dan and Don. Right? There is 1 out of 6 ways for that to happen. So what are the chances? 1 out of 6. Right? So we can create this sample space based on the total number of possibilities, right? There is a way to find the total number of possibilities of a scenario like this using your calculator. It's the choose function, which will be in yes, this one, I think. Yes, all right. So in your calculator, right, when you go to math and you go over to the probability, you choose this thing, it's NCR. All right, didn't do what I wanted to do. I need to figure out how to use this. I don't know if that's, yeah, I did something wrong. I know how to do it on a different calculator, that's the problem. I'll figure out how to use that later, but that function, the choose function, right, in this case it's for choose 2. This is the notation for that. It's the big parentheses with numbers stacked, no bar or anything between. It says out of 4 possibilities, how many different ways can I choose 2 things? 6. If I have 5 possibilities and I was choosing 2, I think that goes to 10. And this returns much larger values for larger possibilities and numbers. Anyhow, I need to show you guys how to create that sample space so you can do one of the problems. Using the choose function on your calculator is not necessary for the example. Anyway, sorry, that took more time than I wanted to. Any questions on this? No? Right. Then our last discussion board for the week and for the month of November. Man. Oh wait, no, notation's good. Okay, good. Sorry. My notation was being weird last night when I was putting this in. Standard deck of playing cards with jokers removed consists of 52 cards in 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards with denominations: ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The jack, queen, king are referred to as face cards. Imagine that we shuffle the deck thoroughly and deal 1 card. Let's define events F, getting a face card, and H, getting a heart. All right. So you'll make a 2-way table that displays the sample space. Across the top, you could say face card, not face card, as the 2 options. That would be F and F complement. And H, as the rows, heart, not heart. Right? And then put in the totals accordingly. Then you will use that to find the probability of F and H and explain why the probability of F or H is not equal to probability of F plus probability of H. And this is based on that general addition rule. All right, so it shouldn't be too bad. If you do have any questions, please let me know. Other than that, that's everything. I kept you guys longer than I wanted to. I do apologize. If there's anything else I can support you with, please let me know.